Welcome to the first recorded video lecture for the course PH3104. As you can see, this course is on electrical circuits and electronics, with electronics of course forming the bulk of the course. But in order to be able to calculate various results with the circuits that we will use, it is essential that we have a firm grasp on electrical circuit analysis, and that's what we are going to start with. So in this first lecture, we are going to recapitulate some of the old stuff that you already know, in particular Kershaws current and voltage laws, and then go on to talk about a couple of derivatives of that well-known system, something called Maxwell's mesh equations or loop equations, and also Norton's method. As I said, these are derivatives of Kershaws method or Kershaws laws. So first, let me quickly recapitulate something which everybody knows, at least everybody in this class knows, the Kershaws laws. So Kershaws laws, what are they? They are basically applications of the standard conservation laws of physics to electrical circuits. In particular, two conservation laws. First, the law of conservation of charge, which essentially says that if there is no charge accumulating in any given region, then the net charge coming in per unit time and the net charge going out per unit time must balance. The charge coming into some place per unit time is essentially the current going into that. So what we are really saying is net current going in must equal net current going out. And if we adopt the convention that we only consider current going in as positive, which of course means that some currents will be negative in value, because of course you can't have all the currents going in. Some must go out in order to maintain that net current going in has to be equal to net current going out. But if we adopt the convention, the sign convention, that current flowing into a point or what is called a node. Okay, technically a node is a place where more than two wires in a circuit meet. So three or more. Net current going into a node must be zero, which is the same thing as saying net current going in is equal to net current going out, provided we adopt this convention that current going out is negative current going in. So in this figure we have drawn a node which has 6 wires carrying current into it, with currents I1, I2, I3, I4, I5, I6, and Kershaws current law essentially says that all these 6 currents added together must be 0. Of course that means that some of them must be positive, some of them must be negative, unless of course all of them are 0, which means some currents are actually going in according to the convention and the negative currents are the ones which are really going out. So that's conservation of charge applied to a circuit, in fact to a particular node in a circuit. To which nodes should we apply them? The answer is all of them, but we will see that we really don't need to overdo things and do it for all the nodes. So that's Kershaws current law. What about Kershaws voltage law? That really is an application of the conservation of charge to an electrical circuit. It's an application of conservation of energy to an electrical circuit. So to understand this, let us look at this cartoon of a circuit here, and let's say we start. This is a circuit with a lot of stuff which has voltage changes. Now these voltage changes V1, V2, V3, V4, V5 have been indicated here. However, I've deliberately not drawn what is it here that is causing the voltage change. There could be resistances through which current is flowing, there could be batteries, there could be other stuff. But right now, these V's are just abstract voltage changes, and the way we have drawn it is this. As you go around this particular loop which you have here, which is starting at this point and coming back to the same point, let's say if we go around clockwise, all the voltages are shown as drops. We are going from the positive end, which is the higher end of the voltage, to the negative end. And what Kershaws voltage law tells you is that if you go around in a loop in a circuit, whichever loop, that is, you start at a point, go all the way around the loop and come back to its original point, then and keep track of what voltage drops you see along the way, each one of them has to add up to, or rather all of them has to add up to 0. Now what has that got to do with conservation of energy? Simple. Just imagine that you are taking a positive charge along with you as you go round the loop. So here, as you go from here to here, the electrical energy stored in the charge drops because it's going to a lower potential. So what happens? Some extra energy is available. Fine. You go round again. Same thing. Although of course, remember, by convention we have drawn all these voltages as drops, but since the law tells you that the total sum has to be 0, some of them must be negative, so there will be rises somewhere. So although I am saying that the electrical energy drops, but that's just conventional. If that happens, if V1 is positive, if V1 is negative, then the actual electrical energy stored in the charge rises. But anyway, as you go all the way around, you have energy, total energy change, or total energy dropped by the charge is the amount of charge times the total change in potential. Now if by the time you go all the way around and come back to your original point, there is a net total change in potential, then what happens? If there is a net drop, let's say, what happens is the net electrical energy of the charge has changed, decreased when you have come back to its original point. That means some extra energy is available in some other form. Fine. But now you see, you are back with your charge where you were at the beginning. So you can keep on going round and round the loop and get more and more energy out every time you go. So that would be free energy for nothing. Perpetual motion machine of the first kind. Of course, you might argue that it might so happen that by the time you have come back to your original position, the potential has actually gone up, which means the energy of the electrical energy of the charge has actually increased, which actually means that it must have absorbed energy from somewhere during its motion. Is that a problem? In itself it is not, but remember, we could, if that were the case, then all I would have to do is take a negative charge along the path, the same path, and I would be able to get free work out of nothing. Or I could take the positive charge and just go the other way, and I would again get free work out of nothing. Since physics prevents you from having free work out of nothing, the net potential change when you come back to your original point has to be 0. I have used the convention that the net potential drop is 0. You could also equally well use the convention net potential rise is 0. Provided, of course, you are careful not to mix the two up. Let's illustrate an application of Kershaws voltage law now to a real situation. What I have shown here is a part of a circuit. All the dashed lines that you see sticking out here, here, here are indications that there are other parts of the circuit which have not been drawn, but I have shown a portion where you can make out clearly a loop. You can start at this blue dot here, go all the way around. I have decided to go around clockwise, as you can see from this dashed arrow that I have drawn here. So I start here, go all the way around this and land up here. In the process, adding up all the voltage drops and equating the total to 0. So let me just illustrate this step by step. As I cross this resistance, notice I am crossing in the direction in which the current is flowing, and of course current flows from higher potential to lower potential through passive circuit elements, through resistors. And here what we have is a voltage drop. since this is a voltage drop and I am adding up net voltage drops, I will count this with a plus sign. That's why this is plus I1 R1. Well, next we encounter the resistance R2 and the current I2 is flowing against the direction in which I am moving. So I am going opposite to the current. That means this is really a voltage rise. Once again, remember, I am counting net voltage drops. So this one will come with a minus sign. The next step, I will be crossing the battery E1. Now I am crossing the battery from the negative side to the positive side as I go clockwise. And because I am going from the negative to the positive end, there is a voltage rise. So again that counts as negative because remember once again I am counting voltage drops. So minus E1 R1. Well, the next one should be easy now. I am going against the current, voltage rise, hence I3 R3 should come with a negative sign. And then I am going from positive to negative end of a battery, a voltage drop. So that counts as positive plus E2. So now I am back where I started. So all of these should add up to 0. So this is how you use Kirchhoff's voltage law. Of course, as I've said before, the fact that I'm going clockwise is a convention. I could have gone counterclockwise as well. In fact, very often people do adopt the convention that you always go around counterclockwise. There's no real reason for that. It's just a convention. Also, I've added up voltage drops to get 0. Well, you could have equally well added up voltage rises to get 0. And you would have ended up with the same equation with every sign reversed. So let's just summarize. The rules for KVL is total voltage drop over a loop is 0. I've highlighted the word drop and loop and 0. Those are important. But of course you could have just equally well said total voltage rise over a loop is 0. Now, for quick reference, let me just remind you that when you are crossing a resistance, the drop is positive when crossing in the direction of the current. When you are going in the direction of the current, voltage is actually dropping in the direction you are going. Negative when crossing against the direction of the current. This is again just what we have seen a while ago. But while across a battery, the drop is positive when crossing from positive to negative terminal and negative when crossing from negative to positive terminal. These are things which you have to sort of get so used to that they should be automatic when you are writing down an equation, especially the Kershaws voltage law equations. Now, of course, you can instead use the convention that total voltage rise is positive, in which case you would have to reverse all the signs above. Well, my suggestion, stick to any one convention so that you don't get confused. Now, there's one question that might be nagging some of you at this stage. How did you know the direction of the currents in the previous circuit? How did I know that I1 is going in this direction, I2 in that, and so on? Well, in some cases, given especially in simple circuits, it's pretty easy to make out which direction the current will flow in. But in some other cases, not so much. Should I really care whether I have got the direction of the currents right before I start writing the equations? The answer is no. You can just assume the currents to be in whatever direction you want. If at the end of your calculation you end up with a positive result for your currents, that means your original choice was right. If at the end of the calculation your current works out to be negative when you solve the equations, it means that you made a wrong choice to begin with. But that's alright, because now you know exactly which way the current is flowing and how much it is. Now let's go in for an application to a real physical circuit, one which you all know. This, of course, is our old favorite, the Wheatstone bridge. And although most of your high school has been spent in dealing with the Wheatstone bridge when it's balanced, as you all perhaps know, finding out the currents in an unbalanced Wheatstone bridge when there is current through the middle branch is not that easy. There are several ways of doing it, but I'm just going to use plain old Kershaws laws, and right now I'm really not that interested in finding out how much the currents are, but writing down the equations which will tell you how much the currents are. So we will use Kershaws current laws and Kershaws voltage laws, both. So first we label the currents. That's our first job. And as I said, do I care which way the currents are? Well, in this case, I know definitely I0 is going to flow this way because this battery makes current flow this way. Of course, we are using conventional current notation, that is current going from positive to negative, as opposed to electron flow direction, which as you all know is in the reverse direction. I will not keep on referring to that very often. You all know that current flow direction is actually opposite the direction in which electrons actually flow in a wire. That said, we will just stick with the conventional current flow notation. So current I0 flows in this way, that's obvious. Similarly, here it's pretty obvious that I1 and I2 will be flowing this way. Same for I3 and I4. No problems there. But what about I5? Do I know whether it's flowing downwards as shown here or upwards? The answer is at this stage I don't care. I will work out the equations that will tell me what I5 is. If it says I5 is positive, it is flowing downwards. If I5 turns out to be negative, that means in the circuit it actually flows upwards. Frankly, I could have actually been pretty random about choosing I0, I1, I2, I3, I4 as well, with the same final idea that if I end up with a negative value, I know I have chosen my original direction wrong. But people usually try avoiding negative numbers for whatever prejudices they have. That's really a childish prejudice. But still, most people don't really like negative numbers that much. So we will try to make proper choices of current directions as long as the directions are obvious. I will not deliberately choose I0 to be to the right here. But frankly, as I said, it does not really matter. So the labeling is done. There are 6 currents in the circuit, I0 to I5, and I have labeled all of them. Now we apply KCL. The same circuit as before. I am just applying KCL here. And how do I apply KCL? Well, I will choose a node, and at each node I will add up all the currents going in. Of course, if a current goes in according to my arrow convention, then it counts as positive. If it goes out, it counts as negative. And I have to add them all together and get a 0. So, first, this node, I0 is going in from the arrow, I1, I2 are going out. So, of course, I0 minus I1 minus I2 equals 0. Let's move on to the next node. I1 going in, I3, I5 going out, I1 minus I3 minus I5 equals 0. This node, I2, I5 going in, I4 going out, I2 plus I5 minus I4 equals 0. And I can keep on going. This node, I3 plus I4 going in, I0 going out, and so on. Well, I've already got 4 equations, and it turns out that not all 4 of these are independent. In fact, I can get a few more. So, the point is, if you keep on applying KCL to every node you see, you will soon get to see equations which essentially repeats of each other. I will leave you to worry about how, for example, you can get the last equation by linearly combining the previous ones. It's sort of obvious, but anyway, and it's also sort of obvious why a particular equation will be a combination of the other equations. But I will let you worry about that. Let's move on to KVL. Well, I will have to identify loops in the circuit in order to apply KVL. One loop I can immediately see is this one, the one marked in red here. And if I apply our law, I am going around clockwise as before. I1 R1 drop, I5 R5 drop, I2 R2 rise. So I1 R1 plus I5 R5 minus I2 R2 equals 0. No batteries in circuit, just voltage drops, current and resistance. Remember, if you are going in the direction of the current, give it a plus sign. If you are going in the opposite direction, give it a minus sign. So next, let's look at this loop. I3 R3 plus, because we are going in the direction of the current, minus I4 R4 minus I5 R5, because these two were against the direction of the current, you get 0. Well, I can take the outer loop like this, I will get I1R1 plus I3R3 minus I4R4 minus I2R2 equals 0. Now, it should be obvious that this equation is what you should be able to get if I added these two equations. In fact, you can just add them in your head and see that this is what is coming around. But that's also should be obvious, because if you take this loop and the next loop and put them together, you should essentially get the outer loop, because whatever this one contributes to the two loops cancels out. So, as with KCL, these are not independent. But let's take this loop for example. So this is slightly different from the previous ones, because now you have a battery in the circuit, but again I0 R0 in the direction, I1 R1 in the direction, I3 R3 in the direction, all pluses. Here you are crossing from the negative to the positive side, which means it's a rise, so comes with a negative sign, minus E equals 0, and you're done. So there's one more equation. Well, there are other dependent loops as well. For example, you can have this one, or you can have this one. You can have others. So there are many ways of writing down KVL, but of course now you have a problem, you have a proliferation of equations, and in this particular circuit it's pretty easy to see which ones will be dependent, which ones will be not, but in a complicated circuit that may be very difficult to figure out. But in the end of the day, you have 6 unknowns here, the 6 currents I0 to I5, and you can write down 6 equations, 3 using KCL, 3 using KVL, all independent of each other. That actually is a bit of a tricky thing, figuring out which ones are independent, which ones are not. And when you solve them all together by using any standard linear algebra methods. Of course, if we are solving 6 equations in 6 unknowns using class 12 like methods of say using inverses of a 6 by 6 matrix may not be a great idea. That would be too painful to do. But things like Gauss elimination, for example, which you must have learned in the previous semesters, should be pretty easy to use and solve. Of course, for more complicated large circuits, this may become quite a big set of equations to solve, and there I would suggest you make use of computer programs. For example, NumPy has methods for solving equations, or the SciPy module in Python has a wonderfully good linear algebra solver. We will discuss this in the discussion class later, how you could use Python modules, for example, to solve the equations that you are going to get. But now that you have studied all this, we have your first class test, which you're supposed to do while you're listening to this video in around say 10 minutes. So this is a real life application of Kirchhoff's laws to a different circuit. So here is the circuit. Please apply Kirchhoff's law to this. Okay, that was a joke. I miss making jokes in class, so this is the best I could do in a video. I'm not really asking you to apply Kirchhoff's law to this mess here, and I promise that your exam questions will be easier than this one. But please bear one thing in mind. Even in such a mess, Kirchhoff's law would still be valid. You just have to know how to use it. Well, this is a really messy situation, but even the ones which you have to work out in your actual real life problems may not be this messy, but would be pretty difficult to work with if you just had only KCL and KVL in your armory. As I indicated earlier, you will have way too many equations. Figuring out which ones are independent, which ones are dependent may be a pain. Of course, using methods like Gauss elimination has the advantage that even if by mistake you put in some dependent equations, Gauss elimination would get rid of them. But That's way too much hard work. So it would help if we had some ways in which we could be sure that we are getting the independent equations directly. And also, we have both KCL and KVL to worry about. Why don't we somehow simplify things a bit? Maybe make KCL choices automatic and then use only KVL. By the way, we often used to do things like this in high school. When we had assigned currents, maybe instead of saying I0 goes in, I1, I2 go out, I say I0 goes in, I1 goes out this way, and I0 minus I1 goes out that way. That way, KCL is automatically satisfied at that node. But doing this for a complicated circuit becomes pretty messy. So we will next describe a method by which this can be simplified a lot. And that is called Maxwell's method. It's known either as the mesh method or the loop method depending on which book you are reading. But the idea is the same. You essentially break up your circuit into loops and assign things called loop currents, which somehow magically take care, okay, not really magically, but they take care of Kershaws current laws automatically, and you only have Kershaws voltage laws to be used.
So now let us try to illustrate this Maxwell's mesh method by using an example. And the example is our old friend, the Wheatstone bridge once again. So, as I said, in Maxwell's loop method or mesh method, we take into account the KCL equation, Kershaws current law equations, automatically. How we do that is break up the circuit into loops and assign what is called a loop current. So basically there are three loops that you can see in the circuit. The one with when you go along R1, R5, R2. Another when you go along R5, R3, R4. By the way, as we have assigned the currents counterclockwise here, so you are actually going around R3, R5, R4 here, and R5, R1, R2 here, and another loop which is R4, R2, R0, E, and crosses all the way and comes back. So these are three loop currents. So here the independent loops are sort of obvious. You can see that these are three distinct loops. And what we do is, instead of assigning currents to branches, you assign currents to loops. What does this really mean? It means that according to this assignment at least, the current through R1 is I1 going this way, going from top to bottom left. On R3 again, you have current going this way, I2. Of course, these are different from the currents that we had assigned in our KCL, KVL calculations earlier. So let's not get confused about the two. But what about current through R5? Now here you have both currents I1 and I2 meeting at the same place. Notice that I1 is going up and I2 is going down at the same time. So current through R5 is really I1 minus I2. Okay. So once you take this into account, Kershaws current laws, as you can easily check, are automatically satisfied. Now, how do you use Kershaws voltage laws in this case? You just apply KVL to individual loops. Right now, for example, I have a loop drawn, the first loop. Now, these loops are the same loops over which we have assigned the currents. Here, I am looking at the loop through which current I1 flows. And let's cross individual resistances and write down the net drops. Again, remember, if you are crossing in the direction of the current, you have a drop. If you are not crossing opposite to it, you have a rise. So, because this is the first time we are using the method, we are going to break this up into steps. But as you will soon see, there's a very easy mnemonic way of remembering exactly what the final equation, or writing down what the final equation is going to be. So here, okay, sorry, I went a bit too fast. You are going through R1 in the direction of the current, so you have I1. Then you are going through R2, but now the current is actually I1 minus I3. I1 going in this direction, I3 in the opposite direction. I1 minus I3 R2. And then you are going again I1 in the same direction as you're going, I2 in the opposite through R5. So you have I1 minus I2 R5 and you're back where you are. There are no batteries in this loop. So these three voltage drops have to add up to 0. So this is basically application of Kirchoff's voltage law. But there is a rather nice trick which makes this look, or writing this down, this equation a lot faster. Notice all we have done is this. You combine the terms together, you have I1 in R1, R2, R5 in these three terms. So if you pull them together, you get something which looks like this. Now what's so great about this expression? Notice that I could have written this down simply by saying multiply the loop current, the current you are currently looking at, in this case I1, by the sum of all the resistances in the loop. So R1 plus R2 plus R5, just multiply I1 by that. And take away from this, subtract all the IR terms for adjoining loop current. So here I2 is an adjoining loop current, I2 R5 comes with a minus sign. Here on R2 on the other hand, I3 is an adjoining current that comes with minus R2 R3. So that's it. Total resistance in the loop times the loop current, subtract from it IRs for the other currents. You don't have to worry about the direction in which current is going, etc. You just follow this rule, the equation will work out. So what about the next loop? I'm just writing down the loop directly now. There are three resistances in the loop, R3, R4 and R5. So R3 plus R4 plus R5 into I2. Total resistance in the loop minus the adjoining ones, R5, R1. R5, I1 adjoins this loop through this branch and I3 adjoins this loop here. So minus R4, I3. And that's equal to 0, no batteries. Notice that this is nothing but Kirchoff's voltage law. Net voltage drop is 0. But it's much easier to write down. Just multiply the total resistance in the loop by the loop current. Subtract the adjoining other loops, contributions on the other loops with minus signs. But the only thing you have to worry about beyond this is what happens if there's a battery in the circuit. And even then the rule is very simple. You just, for example, when you're looking at this loop, the three resistances R0, R2 and R4. So R0 plus R2 plus R4 into I3. Minus R2 I1 because that's an adjoining loop. Minus R4 I2 because that's another adjoining loop. So that's the net voltage drop, which has to be equal to the net voltage rise. And then all you have to worry about is when you're going around this loop this way, which way are you going? Here you're going from positive to negative of the battery. So that's the voltage drop. If you're going to use net voltage rise equal to net voltage drop, or voltage drops due to the resistances equals voltage rise due to the battery, then you have to write the battery contribution is minus E. Of course, you could have written everything on one side of the voltage drop, in which case you would have had plus E on the left. It's usually conventional that when you're using Maxwell's loop method, you use voltage drop due to resistances equals voltage rise due to batteries. And there again the final law is very simple. Just add up all the resistances in the loop, multiply by the loop current for that particular loop, subtract contributions from adjoining loops, IR contributions from adjoining loops, and then equate that to the net voltage in the loop, net voltage rise in the loop as you go around. So which one is a rise, which one is a drop? It's easy. The long end of the battery is positive, short end is negative. Go from negative to positive, it's a rise. If you go from positive to negative, it's a drop. And if there are several batteries, you add up their contributions. So that's it. So now what happens is that you end up with three equations, and these three equations are guaranteed to be independent. And if you solve them, you end up with your loop currents. Here, the point is you don't really get the currents through the resistances directly. What you get are the three loop currents. So if you want the currents through the resistances, then of course you have a slightly longer calculation to do, in the sense that after you have found out I1, I2, I3, the current through, say, the resistance R5 here will be I1 minus I2 going upwards. Of course, that means if I1 is more than I2, it's actually going upwards. If I1 is less, it's going downwards. So that's Maxwell's loop method. We will next discuss about Norton's method, or Norton's nodal method. But before we do that, we need to take a look at some elementary things. Elementary things like what exactly is this battery, or what exactly is this voltage source that we are talking about. And the real reason why we need to take a look at that is, in order to use Norton's method, we need to take a look at something which is slightly less familiar than your old friend, the battery. We need to take a look at current sources and non-ideal current sources. To understand exactly what that is, let us first take a look at something which is more familiar to us, a non-ideal voltage source, which is essentially what a real battery is. As you all know, a battery is characterized by a battery voltage, or what is more precisely called as EMF. But in addition, and this is also something which you all know, a battery is supposed to have a resistance, an internal resistance. Now, what does all this mean? Is it really true that a battery is built with a ideal EMF source in series with a resistance? Of course not. This picture of a battery as an ideal voltage source in series with a resistance is an effective equivalent picture. And why does such a picture at all work? The answer to that lies in Thevenin's theorem, which we are going to study in the next lecture. But we all know what this means in this context. If you connect a battery to a circuit, do you really get its rated voltage delivered to the circuit? The answer is no. If your circuit has a very, very high impedance, that is, it draws very little current, ideally if it draws no current at all, then the voltage delivered by the battery is exactly equal to its rated value, the EMF. On the other hand, the more current the external circuit draws, the less voltage does the battery deliver. So the battery voltage drops as the current delivered to the external circuit increases. How do you model this? You model this very simply by saying that a real battery is actually an ideal voltage source, an EMF source E, in series with a resistance. And what is the job of this internal resistance? Bigger the current delivered to the external world, bigger the drop across the internal resistance, so less voltage gets delivered to the external world. So this is basically it. A non-ideal voltage source, which is every voltage source that exists really, can be thought of as an ideal voltage source with EMF E in series with an internal resistance R, and this E is something which you will get only if you measure the voltage of the voltage delivered by your voltage source without drawing any current, the open circuit voltage. How do you get R? Well, this next thing that I'm going to say is going to come with one of those disclaimers. Please don't try this at home. But in theory, if you could connect a short circuit across the battery, please don't. You're going to burn out the battery and definitely burn the wire or your finger. But if you could do this without burning anything up, then the current through the short would have been E by R, since you have already measured E by noting the open circuit voltage. You get the short circuit current, which is what you get when you current a wire across the two ends. R will simply be the open circuit voltage, which is E, divided by the short circuit current. So this is basically how an equivalent voltage source works. Now what about an equivalent current source? An ideal current source is one which delivers the same amount of current no matter what you connect across it. Just like an ideal voltage source would deliver the same voltage E no matter what you connect across it. In the case of the current source, what happens in reality is, if you connect a very, very small resistance across it, the output voltage is very small. That's of course I into R, so it's very small. And the current delivered to the external circuit is nearly I. However, the more the resistance of the external circuit is, the bigger the voltage you try to deliver, the smaller the current delivered gets. So how do you model that? Well, you model that by a very similar trick as the one which we used here, you model that with a current source, an ideal current source. This is one of the symbols used for ideal current source, the one I'm going to use in this course, a circle with a line drawn across it. The ideal current source would have delivered current I to the external circuit if it were the only thing in the effective circuit. But the effective circuit to a real current source is an ideal current source connected in parallel to an admittance. An admittance, of course, is a resistance whose value is being measured in reciprocal units. So this Y is inverse resistance. Now what does this really do? It essentially does this. If you have a very small resistance connected here, almost all of the current will go through the external resistance. So the entire current delivered by the ideal source, almost in its entirety, will flow to the external circuit. But if the external resistance becomes larger or external admittance becomes smaller, what will happen is the voltage drop across the two ends will increase, which means the voltage drop across Y will increase and the current through Y will increase, which means the current delivered by this current source branches into two pieces, and a substantial part now will flow through the internal admittance. So less will get delivered to the external circuit. So just like in a non-ideal voltage source, more current you deliver, less voltage does the external circuit get because of the drop in R. For a non-ideal current source, the more voltage it produces, less current it actually delivers to the external circuit because of the fact that current gets diverted to the internal admittance. Now for a given source, is it a current source or a voltage source? The answer really is that it can be thought of as either. Just think about it. We said that a voltage source essentially produces a voltage difference E if you measure the voltage across it in open circuit. On the other hand, if you measure the short circuit current, you can find out R from there. Well, if you were given a source and not told whether it's a current or a voltage source, what you could simply do is measure its open circuit voltage, and that would give you E, and measure the short circuit current. When you divide E by that will give you the resistance. Well, if you tried that to your non-ideal current source, the result would simply be this. If you were to connect nothing here, the entire current will flow through Y. So voltage drop across the two ends, which is I times R, Ohm's law, simply becomes I by Y. So effectively, you would be correct in thinking that whatever you have been given is actually a voltage source with EMF given by I by Y. And R, you can easily calculate that. After all, if you were to put a short here, the entire current I will flow to the short. So ISC is just I, short circuit is just I, and you can directly divide EOC, the open circuit voltage I by Y, by the short circuit current I to get the resistance, which is 1 by Y. So if you have a current source, you can think of that as an equivalent voltage source as well. Similarly, if you have a voltage source, I will let you figure it out yourself. It's pretty straightforward. You can always think of it as a current source as well, where the current source has a ideal current source given by E by R. That's the short circuit current, right? Because that's, of course, the current you will get if you were to use a current source. If you short circuit the two ends, the current you will get is I, and that's what you have here as well. If you short circuit the two ends here, you will get E by R. So I is E by R, and very similarly, Y, the admittance equivalent, is 1 by R. So if the same circuit can be thought of as a current source and a voltage source, why is it that we are more used to voltage sources than current sources? At least we have seen way more applications of that till now. The answer really is that a battery is very, very similar, very, very close to an ideal voltage source. It's not an ideal voltage source. It does have an internal resistance, but that internal resistance is typically very, very small. If the battery is any good, then its internal resistance is pretty small. Actually,
when a battery runs out, in the language that we use in daily life, what has happened is chemical processes inside the battery actually ends up increasing its internal resistance a lot. So it hardly manages to deliver any current. But a good battery has a very small internal resistance. A good current source, on the other hand, should have a very small internal admittance, so that very little current is diverted through that branch. And you can know this through the equivalent connections here, that these two demands are contrary to each other. A near ideal voltage source with a very small r would be equivalent to a current source but a very poor current source. A near ideal current source would be equivalent to a very poor voltage source. So, near ideal current sources can be manufactured in the lab, and there are actually near ideal current sources, which we often call just ideal current sources, in our laboratory as well. But near ideal current sources are much more difficult to manufacture, they are costlier, and they are not so common in daily life. Near ideal voltage sources are more common, but voltage sources and current sources can be treated interchangeably by using these equivalent relations. The one other important point that I have to make is this: there's only one case where you cannot replace a voltage source with an equivalent current source, or a current source with an equivalent voltage source, and it's pretty easy to guess what that is. An ideal voltage source, not a near ideal one, but an ideal one, has R equals 0. That cannot be replaced by an equivalent current source, because then these equations, which will tell you the parameters of the equivalent current source, becomes, well, they give you absurd results. They give you infinitely big I and infinitely big Y. Similarly, an ideal current source which has Y equals 0 cannot be replaced by an equivalent voltage source. In all other cases, this equivalence works fine. Only for ideal sources, if it's an ideal voltage source, it has to be treated as a voltage source always. It's an ideal current source, it has to be always treated as an ideal current source. So with this background, let us now go and take a look at Norton's method. With the background about current sources and equivalent voltage sources in place, let us now move on to the last topic of the day, which is Norton's nodal method. Now, what we are going to do is we are going to use the same circuit here, but with one change, or rather two changes. Just for convenience, we are going to replace each one of the resistances with the corresponding admittances, just the reciprocal. So R1 will be replaced by Y1, Y2, R2 by Y2, and so on. And the circuit symbol of an admittance is the same as that of a resistance. So the circuit will look more or less the same. The labels will be Y1, Y2, Y3, Y4, Y5, Y0. But more importantly, what I will have to do in order to use the method is replace this voltage source, which is in series with this resistance, with the equivalent current source. That is, E will be replaced by a voltage source I, which is actually E by R0, in parallel with the admittance corresponding to this equivalent source, which is 1 over R0, which I am going to call Y0. So this is the circuit now. Everything else remains the same in the Wheatstone bridge, except that the voltage source in series with a resistance has now been replaced by an ideal current source in parallel with an admittance Y0. In Norton's nodal method, what is done is it takes the Kershaws Voltage Law equations into account automatically, so you don't have to write them down. All you have to write down are the current law equations. So this is in a sense just the dual to Maxwell's method, where you did not have to write down Kershaws current law equations, they were taken care of automatically. You just have to write down voltage law equations. Here is the other way around. So what you do at the beginning is you first of all identify all the nodes in the circuit. Nodes, remember, are places where more than 2 wires, 3 wires or more meet. This is one here, this one is here, another one is here, and the one is here, and so on. So here in the circuit there are 4 nodes, and what we do is we assign voltages to the nodes V1, V2, V3, Well, actually voltages to all nodes but one. In this case, V4 is chosen to be a node at 0 voltage. So we will assign voltages to n minus 1 of the n nodes. One of them will be arbitrarily chosen to be the 0 voltage node. So we have to write down equations which will help us determine V1, V2, V3, and these are the nodal equations. How do we write them down? Well, simple. You just apply Kirchhoff's current law to each node in turn. So for the first node V1, the one for which the voltage is V1, notice that current can flow out from V1 towards V2. The potential difference across Y1 is V1 minus V2, and the current through that is just V1 minus V2 into Y1. This is Ohm's law. Although we are used to thinking of Ohm's law as V1 minus V2, the voltage difference by the resistance is also V1 minus V2 times the admittance. Now, this is something which is very elementary but which has to be stressed because very often people get confused about this. In Ohm's law, what you have is not voltage into voltage by resistance is current. What you have is voltage difference by resistance is current. And that is very important to remember. So here is V1 minus V2 into Y1. Then there's another way in which current can go out, which is towards node V3. That's V1 minus V3 into Y2. That's the current which is going out again. Then there will be another one as well, which is current will flow out through Y0 towards node V4. So it's V1 minus V4, but V4 is 0. So it's just V1 into Y0. So these are the three currents going out of the node. And the current I, the current carried by the current source, is going into the node. So these three currents going out of the node has to be equal to the current I. So this is your nodal equation. And just like in the case of Maxwell's mesh equations, there is a quick way of writing them down. All you do, and you can easily see that by gathering the terms together. Notice that this simply says this: take the voltage at the node which you are focusing on, multiply that by the sum of all the admittances which are joined to it. So this node has Y1, Y2 and Y0, these three admittances joined to it. So get Y1 plus Y2 plus Y0 into V1. Subtract from this admittance time voltage for all other nodes which are joined to this node. So V2 is joined to this node, so is V3, so is V4 by the way, but V4 is 0, so that doesn't count. So minus Y1 V2 minus Y2 V3. So this stuff has to be equal to the net current going in due to any current sources. That's it. So quickly, now we can use this rule to figure out what is the equation for node V2, marked V2. And in this node, of course, Y1, Y5 and Y3 are the three admittances joined to it, and V1, V3 and again V4 are the three voltages which are connected to the node in some way. So the equation will simply be Y1 plus Y3 plus Y5, the sum of these three admittances into V2, minus V1 into Y1. So the other voltage which is joined to it has to be multiplied by the admittance which is joining it. So minus Y1 V1 minus Y5 V3. Of course, also minus Y3 V4, but Y3 V4 is 0 and no current is going into this node. So this net current going out is equal to current going in, which is 0. And then we have to write down the nodal equation for V3, which will simply be Y2 plus Y4 plus Y5, these three admittances into V3 minus V1 into Y2. So adjoining nodes, voltages of the adjoining nodes times the corresponding admittances minus V4 into Y0, that doesn't count because V4 is 0, minus Y5 into V2, and since no current is flowing in, this is equal to 0. So once again, you should be able to write down the nodal equations without any thought. You can write them down almost near automatically. Total admittance of all the wires joining to this particular node into the voltage of the node minus adjoining node voltages times the admittances joining them, and that's equal to the net current going in.
So now you have three equations for the three nodes. Solve them by any linear algebra method that you prefer, and you can find out the voltages V1, V2, V3. Of course, if you want the voltage differences, which is really what is physical, say what is the voltage difference across Y1, then you have to answer V1 minus V2 once you have found out V1, V2, V3. Similarly, if you want the current through Y5, for example, once you have found out V2 and V3, it will be V2 minus V3 by Y5, sorry, into Y5. Please remember not to make the mistake I made right now. Ohm's law, of course, is voltage difference by resistance, but it's also voltage difference into admittance. So in this lecture, we have seen Kirchhoff's laws, we have recapitulated them. We've also learned two relatively newer methods, at least relatively newer to most of you, Maxwell's mesh method and Norton's nodal method. And in the next lecture, what we are going to do is we are going to take a look at one-port theorems, Thevenin's equivalent and Norton's equivalent, same Norton, but a different result. And we are going to make use of those to analyze other circuits. Bye till then.